Hello everyone and welcome back. Today's lesson is going to be on the Chatelier principle as we continue with the equilibrium unit. And it perhaps sounds a little more daunting than it actually is. So it's really just how a chemical system responds to a stress. Okay, so talking about stress, and we're going to be looking at then also this shows a stressor being a winter storm or the cold, and how that relates to a chemical system is that we can also think about increasing or decreasing temperatures as being stresses, increasing or decreasing concentrations of reactants or products that can be a stress as well, or changes in pressure and volume too. So if we were in class, you would usually talk right now about a storm. When I was in high school back in 1999. One to remember for sure. Interesting storm here. Mayor at the time of Toronto called out the military to help. It was quite a storm. So what do you normally do when you're cold? Now, a few things you might do. Some physiological responses that might take place is that you might shiver, right? Your cheeks or your skin that's cold or exposed might turn red, and all of these are responses, physiological responses for your body to try to compensate for that cold and to become warmer, to get warmer. Okay, so essentially that's the same thing here now applied to a chemical system. So if a system is at equilibrium, let's change pens here. If it is at equilibrium, and if that now system at equilibrium is subject to an external stress, and that can be a few different things, which we'll talk about. What will happen to this equilibrium, it will either move in a forward or in a reverse direction to compensate for that stress. And whether it moves forward or reverse will be dependent on the kind of stress and the kind of chemical equation you're working with. So the three, because these are practically, they're really related, so I'm going to count them as just one. The three stresses we're going to be looking at for the course is temperature change. Now that can mean increase or decrease in temperature. Also a change in concentration, so a certain reactant or product can increase or decrease in concentration. And then finally, a change in pressure and volume. Now this would occur for the entire system, so you would increase pressure or decrease pressure, increase volume or decrease volume. But we know that pressure is inversely proportional to volume, right? Back to grade 11 atmospheric chemistry, we know that if you increase pressure, you decrease volume. See that inverse relationship there? And if you increase volume, you're going to decrease pressure. So imagine making a canister that's under pressure larger. Well, now that pressure has decreased. So they're inversely proportional. Okay, but let's actually get into it. Before we do though, just a reminder, catalysts don't affect the position of the equilibrium, right? If they're going to reach equilibrium at a certain KEQ value with certain concentrations, then that doesn't change. It just helps get there faster. Okay, so here are some examples that will help us understand how a system could respond to a chemical change, rather how a system will respond to a stress. Okay, so this is our reference formula. Now, if you add a hydrogen gas, okay, so now this is a change in concentration. We're increasing the concentration of a hydrogen gas in this case. Okay, the equilibrium will then shift to what direction? Your options are to the left in favor of the reactants or to the right in favor of the products. If you increase hydrogen, the opposite's going to happen to compensate for that stress. So the direction that this reaction will have to move in, it would be in the forward direction so that that extra hydrogen gets consumed. So increase in concentration shifts then the equilibrium to the right to compensate for that added reactant, right? Moving to the right would convert that reactant to more product, thereby compensating for that increase in hydrogen gas concentration. Okay, so I've hopefully explained that to your satisfaction. I'm going to explain it or maybe explain it less perhaps, or give you some more time to think about it for the next couple of examples, right? So here's one more, or the second one. All right, so now if you add hydrogen iodide, product now, so we've increased now the concentration of product, the equilibrium will shift to the, again, these are great sources of communication questions where I could ask you something just like this, but then ask you to explain why you chose the answer as left to right. Okay, That's no, I was right in selecting that. Okay, so if you've increased HI product to compensate for that increase, you're going to move to what direction? Hopefully you're thinking right now. That is the left. Okay, so the left will then consume product, which is what you'd like to do, because if you've added more of this, you want to consume that. So you've consumed product here, and it will then move to the left in the reverse direction. Last example for this. All right, so now here we have increased in the first two examples. In the last one, we're going to decrease the concentration of iodine gas. So if you've decreased that, the opposite's going to want to happen. So what direction should the reaction move to produce iodine gas? Okay, let's think about that. If you go, hopefully you're thinking of the answer right now, but if you move to the right, you'll be decreasing this because more product will be made. And you don't want to do that. You've already decreased that. You want to do the opposite. If you move to the left, you're going to decrease the concentration of product, but increase your concentration of your reactants, which includes iodine gas. So that seems to make sense. You're then going to shift to the left. There you go. Okay, so those are changes in concentration, and here's a big idea. So a change in concentration will shift the equilibrium towards the end that will compensate for the stress. That's a good statement for practically all kinds of chemical stressors. An example here is if you have reaction A to B, and if you increase A, you're increasing A, the forward reaction is where that shift is going to occur to compensate to use up that extra added A reactant. Okay, next, pressure. So we've looked at concentration, now we're looking at pressure. Important to say here that pressure will only have an effect on reactions that involve gases. Okay, now you will see in your homework that there will be some reactions that you'll go over where perhaps one of these reactants is a solid or a liquid or even aqueous, right? But then the rest of them are gases, right? We can go over those in our live lessons or just ask so that we can clarify, but hopefully you'll know what to do after we go over a few examples. Okay, so here, if you increase or decrease pressure, or volume, really, what's going to happen is, let's focus on this. Let's focus on increasing pressure. It will shift to the side of the reaction with the fewest or least number of moles. So all you do here is you count the coefficients in your balanced reaction. So there's an imaginary 1 here, and there's a 2 here. All right, so on our left hand or reactant side, we have 3 moles of gas, right? 1 of A, 2 of B. In our product side, we have 1 mole of gas C. So if you increase pressure, the shift is going to move more to the right because the right side has less moles of gas, right? Increasing pressure, you always want to do the opposite, move to the side with the least number of moles of gas, and in that case, in this case, the right-hand side. Okay, if you decrease pressure, or inversely increase volume, you're then going to shift the equilibrium to the side with more moles of gas. So in this case, it would be to the left. Okay, so that's how pressure can affect a chemical reaction or a chemical system. All right, so another summation here is a change in pressure volume will shift a reaction to the end that will alleviate the stress by favoring the side with more or less moles. So it's important for you to make sure that that equation is balanced so you can figure out how many moles are on either side. Now there are a couple of situations here that you might run into. If the number of moles on the reactant side is equal to the number of moles on the product side, then effectively you will not see a change because of any kind of a stress, pressure or volume stress. Or if you add an inert or non-reactive gas or gas that is not involved in the reaction, this will assume, or rather this will not have any effect. And I'm jumping to this point, assuming though that there is no change in pressure. Okay, so that's an important assumption to be made, even though it may not be a practical one. Okay, so last, changing temperature. If heat is added, should probably, after finishing our thermochemistry, to change that. If energy, let's say that, if energy is added. Now, you don't just add energy to one side, left or right. It's added to the whole system. So keep that in mind. That's a common mistake. So your equilibrium will shift to absorb that added energy. Okay? If the opposite will happen, if you take away energy, it'll move to the side that produces more energy. So the direction depends on if the reaction is exothermic or endothermic. You can memorize what happens with an exothermic or endothermic reaction. If you increase or decrease, it moves left or right, but it's best not to memorize. It's better just to understand. Okay, so in this example, we're going to increase temperature. So if you've increased temperature, now this is the fully balanced reaction. Maybe we should, again, correct this and we should say energy, but you get the idea. Okay, so if you increase temperature, so the whole system is increasing temperature, what direction is it going to move in? This is an exothermic reaction, right? This is exothermic. We can see that as a result of this reaction, energy is being released in the form of a product. Now, if you increase temperature, it's going to move to the side that decreases this energy, which should be, I'm hoping you're thinking it's to the left. It'll favor the reactant side. Now, a trick that I'd like to share here is treat energy or heat. Sometimes it's mistakenly called heat, as you saw. Treat energy or heat as if, because it's actually not, but as if it were a substance or a chemical. So that means if you increase energy on this side, it's going to need to be consumed, so it's going to move to the left. Okay, that's a little trick that I use as I'm thinking through these questions. Okay, if it's endothermic, then the opposite will happen. The forward reaction would be favored. That's for an exothermic. All right, we've seen how equilibria can shift left or right. Now that also means something else. It means that your KEQ values will increase or decrease. So if the reaction is exothermic and your stress is to increase that, we've seen that the reaction is going to go in the reverse or backwards directions and the reactants are going to be favored, right? Knowing that KEQ is represented by products, right? Products over reactants, right? That means your KEQ value is going to decrease because if your reactants are favored, this denominator increases in value if they're favored because of the Chatelier stress, then your KEQ will decrease. Opposite happens for an endothermic reaction. If your forward products are favored, while the numerator gets larger, that means your KEQ will increase, right? So that's how your KEQ can become affected by increases and decreases in temperature. Specifically temperature in that case, but in any stress really causing a shift, it will change your KEQ value. Okay, last couple of examples, and I'll go over this one for you. So hopefully this is big enough. Maybe I'll make it a bit larger. Okay, so hopefully that helps. So here's a question like this usually appears on a test, by the way. Here's a graph that shows you the concentration of reactants and products over time. You can see that at time 0, they are not at equilibrium, but at some point in time right here, equilibrium is reached. But then, actually, let me change that. At some point in time, roughly here, equilibrium is reached. At this time, though, that a stress is added. So we'll change that. Let's say that's a stress. Okay, in this case, temperature is decreased. Now look what happens when you decrease temperature. But first, actually, before we get into the results, let's look at what's happening here. This is an exothermic reaction. So hopefully you've exothermic, there we go. Hopefully you've realized this is an exothermic reaction. We see that energy is being released as if it were a product. So if you've decreased temperature, now if you think about this, think of energy perhaps as if it were a chemical, even though it's not. If you decrease this, you're going to want to produce more of it. So that means it's going to shift to the right. And look, this is what we see in our graph. We see an increase in product, right? Increase, looking at the wrong thing there, increase in product. And we see a decrease in reactant. Decrease, decrease, because the shift is to the right. Okay? Next, I don't have the answer here, so I'm going to explain what's happening, and then I'll give you a moment to try to answer this yourself. Okay, so this is not an exothermic reaction. Instead, this is an endothermic reaction, and we have products and reactants, right? We have two products here that start at a concentration of 0. We have one reactant here, product and reactant. Beginning at time 0, we have our reactant starting off at a higher concentration, and then it begins to decrease while products increase. And it looks like equilibrium is reached roughly along this point, right? But then a change happens. A stress, I should say, happens. What is that stress? Okay, so there's a few things that we can refer to. Specifically, though, refer to the stress as being a temperature stress. So what happens, an increase or decrease in temperature that causes this change? Now let's review this. What's happening afterwards? See CO2. CO2 is a reactant that has gone up after the stress. And look, our products, they have gone down. Okay, that means our reactant side is favored. That means the shift is then to the left. Okay, so what could that temperature stress be? You really only have two options. Are you increasing or decreasing temperature? Okay, this is an endothermic reaction. So let's think. If you increase temperature, treating as if it were a chemical or a substance. If you increase this, you're going to want to do the opposite. It's going to then move to the right-hand side to consume it. Right, so if we decrease temperature, to compensate for that decrease in energy, treating it as if it were a substance, it will then move to the left-hand side, and that seems to be what's happening. So it looks like, made that line there, it looks like it's shifting, so the shift to the left, therefore a decrease in temperature. Okay, to make up, to produce more energy because of that decrease in energy as your stressor. Okay, what else could happen here if it weren't a chemical change, rather a temperature change? If you're shifting to the left, it could have been that you increased concentrations of your products of either carbon monoxide or oxygen gas. Those could have increased. So then to decrease that, you would move to the left. That could be a change. You could have also changed pressure. Let's see here, 2 plus 1 is 3. You have 3 moles here. You have only 1 mole here, right? So a shift to the left would have meant an increase in pressure. So you could have also said an increase in pressure if I didn't restrict you in asking you to choose between temperature change and being up or down. But an increase in pressure could have also caused that response to this stress and increased temperature. Okay, so hopefully that was okay for you, and you can then start practicing your homework. Here it is. Okay, hope this helped. Post any questions you might have.